The separation is L. And inside this parallel plate capacitor, you have like a cylinder. It's a shell. It's a shell. It's a thin shell of charge. And so now this is radius. So, okay, so let's just maybe think for a second here. And it has charge per like lambda. Okay, so maybe just for you guys to get warmed up here a little bit, let's maybe sort of write down some questions we want to put here. Okay. Yeah. So first, we want to find a potential, let's say everywhere, but at some point z. Rho is the distance from the center. Okay, and z is, say, this is z equals 0. Okay. Center of the Mars. So how about we just start by sort of writing down all dimensional parameters. It's always a good place to start. Okay, just write down, just do it now. Okay, write down all dimensional parameters. Okay, in the problem, what we want to find, rho. Okay? We want to find the potential at this point. It's always a good idea. Start there. Do it. Okay, and then after you've done that, okay, start thinking about the relationship between those parameters. Okay? So ask about what are the boundary conditions. What else? Also, closely related is to say, you have the jump condition, right? So what's the relationship between the inside and the outside? Jump condition. Okay, so why don't you guys think about that for a second, and then we'll go over. And finally, try to guess what the solution looks like. Okay, this is the third, this is some in-class problem. So try to guess a little bit what it looks like. Let's take z equals 0. Okay, so phi of rho z. Okay, so right in the center. Right? Try to guess what this setup looks like. And let's work in a specific limit where, like L is much, much greater than R. So it's, okay, and what else? So to say, now when you start thinking about this problem, right, you want to think about carefully about what happens with rho. So rho is another parameter, it's another dimensional parameter. And the solution will look very different depending on, for instance, whether consider these regimes. And so this is the way theoretical physics works. Okay? So just sort of pretend that R is infinitely smaller than the length. Okay? And you imagine that situation, and then you work out that situation, which usually you can do analytically, okay? And then you sort of step back from that just a little bit, and that's usually pretty good enough to the real situation, okay? Okay, so why don't you guys get started? Write this down.
So where are we defining the zero potential at?
Yeah, so well, you can always add a constant.
Okay, so wherever.
Wherever you want.
Why not everything?
Yeah, why not at infinity? Yeah.
Are you specifying any conditions on the place of the surface?
They're grounded, yeah, they're grounded. Let's say, let's take it 5 to 0, okay? 5 to 0. Meadow plates, constant. It's constant meadow plates. Let's just, so this is supposed to be about 5 minutes of class. Okay, so start writing. I want you guys to start writing. We'll think about it for just a second. The charge is this lambda, right? So you know that somehow the potential has to be proportional to lambda. And then you can choose, let's take the potential at z equals 0 to make it a little bit simple. Okay, so phi evaluated at z equals 0. Okay, so then there's only, if I specify that I only want the potential at z equals 0, then there's only fewer parameters. Okay, so then we have lambda. Okay. Lambda has charge per length. Electric field has charge per area. Okay, so you need to take one length scale outside, right? R. And then there's some function of the dimensionless combinations that you have left over, right? Which is, in this case, just rho over R and L over R. Nothing else. Or R over L, doesn't matter. Okay? So that's it. Right? So you know it's going to take that form. Okay? Before you start. Okay, what about this one? Boundary conditions. Go ahead.
Isn't the potential in charge per length?
But the electric field in the right, so I did electric field somehow. I said electric field, but I should have chart. Potential as units charge per length. Okay. Good. So you sort of know that, right? Now, and then we have to figure out this function. Right? Now, what about the boundary conditions in phi? Yeah. Very good. Okay, so, well, first of all, let's qualitatively, you get some minuses, right? And they sort of screen this. They sort of screen this pluses, right? Because why not? They'll sort of flow there. Okay. And now the boundary conditions. So we first have that phi is 0 on the plates, right? So that's phi is 0 on the boundary. And now the jump conditions, right? So you're supposed to know, I know that if I take any surface and I look here, draw a little Gaussian surface, first of all, then you'll get there. E n dot E minus n dot E n is sigma, right? And in this case, the n is in the rho direction. You get E rho out minus E rho. And the charge per area, right, is lambda divided by 2 pi r. Okay, so that's boundary conditions. So that's starting point. Okay, so we have these two things that we have to solve. Okay. Now, what about this thing? What does it look like? Okay, so we're back here, right? So we're in this limit. Let's take the first limit, that L rho much less, L much greater than R. And we look at the first one. In which case, L is like infinitely long, and looks like this, right? So far away. Right? This is whenever people write this, they mean like take it to infinity first and then step back, right? So we're really, then it's so far away, I don't care. Like this is a charged cylinder, okay, one plate is at the moon. I mean, this is what you should do, right? One plate is at the moon, one plate is at Earth. Okay, and I have a charged cylinder that long. Okay, in which case, I don't care if the plate is the moon, right? I have just an infinite charged cylinder, and I know the answer, right? So in this limit, I just have a charged cylinder. You can use Gauss's law, okay? And you know that the potential just is lambda over 2 pi r. The log of rho. Rho minus lambda. Outside. So you know that. And inside, of course, it's just a constant. You have a charged cylindrical shell. Inside the charged cylinder side, you just get a constant phi minus constant. So that will go, I mean, so you should, whatever solution you go find for this more general problem, in some regime, this should be approximately valid, okay? And that'll be fine as long as rho is less than this parameters. I mean, as long as rho is much, much less than L, right? When rho becomes comparable to the spacing between the plates, well, then you have to recognize that the boundary is there, right? And somehow you start to feel the boundary, right? But in between, you're going to get a rho much, much greater than L, okay? Then you really hardly see.
So how do we determine the constant? Because here we seem to have specified where phi should be 0.
Yeah, I mean, you can't. If you take really L off to infinity, you can't determine constant.
Okay. So it's sort of just
Arbitrary.
Okay.
Is what, somehow the potential is arbitrary. If you have finite L, then you can know about the boundaries of infinity, and then you can set the boundary of infinity to be 0. That will be fine. But in this regime, it's purely convention. Okay. Okay, and so then finally, if I really go to this limit, where rho is like this, right? Then, somehow the cylinder looks like this, some plus charge. Right? And we're sort of way out here. No, okay. So at that point, it just looks like a point charge in a parallel plate capacitor. You don't really realize that there's actually a rod there. Okay, you don't see it at all. Okay, and I don't know how many of you know this. I mean, if you put a point charge, we did a problem like this, right? If you put a point charge in a parallel plate capacitor, it gets screened exponentially. The potential falls exponentially. So you know that it should go somehow like e to the minus rho, and then it should be the nearest scale, like rho. Okay. Good, something like that. And the charge, then dimensional analysis would tell you that it goes like lambda. Somehow should go like that. Potential should go something like this. Good. So we can work on that, figure that out a little bit. Okay, so the overall picture would somehow look like this. You would expect, based on kind of pure thinking, almost no physics, you kind of expect something. And inside the cylinder, so this would be rho over r. This is one. Inside a cylinder, you have a constant, right? Constant potential. So you have a kind of constant here. Then you get a log, somehow log behavior. Just land a log. Constant. And now if you go way, way out here, right? Say when this rho over r becomes of order L over r. Okay, then you expect it to decrease exponentially like this. that's sort of what you basically expect. Okay?
How do you know that the potential is constant inside?
Yeah, so if I take just the limit, I mean, rho is, take rho of order R much, much less than L, right? Then you just have this infinite shell of charge. And you know for the, you can solve this problem with Gauss's law, say, the potential from an infinite shell of charge. And inside a infinite shell of charge, the potential is just constant. You can just, once you draw a Gaussian surface, calculate the electric field. You don't see any electric field, okay? And so if I integrate the electric field to find the potential, I get a constant number. Okay, so that's what we expect, okay, roughly. And then there's sort of corrections each time. Each of these pictures will have corrections, which are like order, say, order R over L. So maybe it's not exactly constant. Something small, which is order R over L, okay, and some other things. Okay. So that's the picture we got to go figure out. Okay, now we have some understanding of that. So we'll go do this. Okay, so let me hand out this thing. We'll go figure it out. Already printed it out. Look at the answer we're going to work for. Okay, a little bit. So then you have some sub-asymptotics.
Nice potential.
Those are minus R. So if you put there R, then you put e to the minus rho over R. That's much, much larger than e to the minus rho over L. I mean, much smaller. I mean, the exponent is much. Just think about that, right?
Well, I mean, you could also have like some function of R and L
Yeah,
together in the exponential.
absolutely. So you, of course, expect some power corrections, some powers plus function of R over L, right? But if R is much, much greater than L, okay, this is a good discussion. Let's maybe broaden the scope. So the question was, wouldn't you expect some function of R over L there, right? Or wouldn't something, wouldn't
There's
it,
some R's
some R's and
and L's.
L's entering? Sure, you would, right? So you would basically, but that's where the power of analysis comes in. So you would say, well, it goes like e to the minus rho over R, and then there's some function of R over L, right? What else could it be? And now R over L is a small number, right?
Well,
So
could
you-
it possibly have like top inverse powers?
So you would potentially have inverse powers, so you expand it, yeah. E to the minus rho, if it's a regular function, you would get sort of f of 0 plus. Etc. So certainly, I would expect power corrections for this result. Right? So it's only in R over L, this is a small number. I only take the leading term, which is f of 0.
Yeah, wait, well, what do you possibly have like inverse powers?
Yeah. Well, okay.
I mean, I'm sure there's some like intuitive logic you could just use.
analyticity of the function, that would be a non-analytic function of R over L. So you have to somehow justify why you would expect a non-analytic function of R over L. Right?
I mean, I don't see any-
Could vary, you would have to have some physical reason, that would be a non-analytic function. You would have to have some physical reason why you would expect some non-analytic function.
Well, we want the unphysical limit of R equals 0 where that, went to 0. I might expect a non-analytic solution.
So if you take R, well, okay. I don't know, would you?
Well, I mean, I don't know, I'm just thinking like some intuitive reason, that
I mean-
only L should enter into that exponential.
Why do you think that somehow, if I keep the charge fixed and make it smaller and smaller, oh well, that I somehow get something which goes up there?
Yeah.
If you made the charge also increase as a function of R, so then maybe, right? Okay. But if you just say, oh, let me keep the charge fixed and in fact, you actually sort of know more. I mean, phi is solving the Laplace equation, and so it is a harmonic function, and so it's completely analytic. Right, so there's really no reason. Okay, good. But of course, you can always verify the computation. Which we do that. Okay. Yeah. Go ahead.
So why I'm surprised that this potential does not depend at all on R. What,
It is. It does.
what is R?
I fixed it to be 10.
Oh, I see.
Right? I mean, the ratio, I fixed the ratio to be 10.
Said that's, okay.
Right? If you change it, then you get somehow a slight change in this picture.
Oh, I see, okay.
Um,
Wait, down here on the example, it's supposed to be rho over L.
Rho over R.
Oh, okay, so not related.
No. Right. So I chose R to be, you can always choose one of them to be 1, right? So I choose R to be 1, and then L is 10. Okay, good. I think that was productive somehow. Okay, so let's go on. Okay, so let's see here. Okay, so now I go solve. Okay, so we're solving. Now we're sort of brutal, right? So we sort of solve here equals 0. Okay. So both inside and outside of the cylinder, you can solve just the Laplace equation. You can find a solution both inside and outside. You have a jump condition, which relates the solution on the interior and the exterior. You can relate the two solutions on the interior and exterior, and then you'll know the whole thing. So let's first do that. So we use cylindrical coordinates. Right, so we get -1 over rho, partial rho, away, partial rho. Okay, minus 1 squared. Something like this. Okay, what am I doing? True, but not what I wanted. There's no dependence on phi, but so there's no dependence on phi, but so we can ignore that. Right? Okay, now I separate variables. Here you would separate into some function of rho and some function of z. I will disastrously call my function of rho r of rho. Then phi, you would just try some separated solutions. Of course, the real solution is the sum of these. So, as I said, we already used capital R, but it should be relatively clear. The radius of the function. good. So you try this. Again, the procedure is always the same somehow. So you plug it in. You look at, for instance, you're going to get some separated equations for L and for R and Z. Okay, so what do we get there? So okay, let me do minus partial 1 over rho, partial rho, k squared. Right. K squared. Looks good. Okay, and then from this other one, separated equation, you get minus partial z squared. K squared. I think that's looks good. All right. So you can kind of do that yourself, right? I mean, from this one, you get that each of these terms is equal to a constant, okay? And that's this k squared times z. Okay. So those are your kind of separated equations, right? And now you got to solve for these guys, these functions, right? The z and the rho, right? And so this one looks harder than this one, right? So we start with this one, okay? Right? It's a good reason. That's a good motivation, right? So starting with that one, I know the solution. Okay, so z is equal to sine and cosine, right? Cosine of z. Just a small comment, maybe I put here, principal these could depend on k, right? Okay. Just a small comment. if k, at this point we know nothing about k. It's real, complex, okay, and even 0, okay. And in the case when it's 0, you would get potentially a different solution, which is just a constant plus b z. So at that point, at the level of this analysis, you don't know anything. And you could understand, the b as being, maybe I should switch it. Maybe I'll write a0 z plus b0. And you could maybe understand this as the limit, that k goes to 0 of these functions. Okay. So okay. Now, if now I have to put some boundary conditions on. Of course, we require that it be 0 at the edges of the plates, okay, and that leads to somehow boundary condition, right? So somehow we want it to be 0 at the edges, okay? We also know from symmetry that it's symmetric, right? That you only can have, the sign is odd and the symmetry is probably symmetric. So, well, it means I can eliminate this guy, right? Eliminate this guy. Okay. And now we also know that the boundary conditions are that should be constant, it should have vanished, right? And so that leads to a quantization condition on k, right? So we get there, just our solution, z of k of z is some constants, cosine k and z. It should be what? And sure, 2n plus 1, okay? Plus 1 L times y. Right. Okay. So we get sort of only specific values of k that this is allowed, okay? First one being n equals 0. Okay, n equal 1 with percent is. That's not right. Okay. Okay, now, so once you have these functions, you know the z's, you know the allowed values of k, you can go ahead and return to the more difficult equation. So this is, return to this z equation. Now, so I go back here, now I know k, right? So the eigenvalue problem was in the z direction. So my eigenfunctions here are the zk's. In this direction, I don't expect an eigenvalue problem. There's no quantization there. Okay. So we're really talking about, again, we construct the propagators, the eigenfunctions like this way, that's my z of k. I'm constructing the propagator into the row direction, which always propagates outward from the boundary. And there's no quantization there. You wouldn't use eigenfunctions. Okay. Okay. So in this case, you solve this beast, right? So okay. Well, looking at this crazy equation, you would find R. Okay. For instance, many things you could do, but one thing you could do is take such a beast and plug it in Mathematica. Okay? Unfortunately, it gives you J0 and Neumann N0, but that's not what you want because you get the wrong solution that way. But you actually want the modified Bessel functions, right? Which are I0 of K rho. Some function. C1. So the general solution takes a form like this. Okay. Good. All right, so that's our equation, and we now know the form of the solution. So the generic form in cylindrical coordinates would be a sum over n. Then you would have C and C. Maybe I use different symbols, C and D. Okay. C and I0, K, rho, K0, rho, and you have this Z. Okay, good. All right. K. So K takes on this discrete values. Okay. So far, so good. So now we have to look at this just a bit further, okay, and try to think about it. Okay. So we have to know something about these modified Bessel functions, what they look like, something about them. So the quickest way, of course, is to ask Wikipedia or make a graph, and that's a good way. So eventually you know what they look like. Okay, so we look at I0 of x. So I0 of x is actually exponentially, so it's kind of like sine and cosine. So Bessel functions are like sine and cosine are e to the I x. And if you go to imaginary arguments, which is what these modified Bessel functions are, it's like e to the plus x and e to the minus x. Okay, so very analogous. Okay, so e to these Bessel functions, I0 is growing at infinity. Okay. It's asymptotic form we can write down a little bit. Okay, so e to the x. Forget about these numbers. I have it here. E to the x over square root of 2 pi x. So it grows like this. And at small argument, it actually approaches a constant, which is 1, which eventually chosen. Okay, in between, you get something. 1 plus x squared over 4. Okay, and here you get e to the x. X much greater than that. So that's what I0 looks like. K0 looks somehow similar, okay? But reverse. Okay, so it looks similar but reverse. So somehow it diverges it at x equals 0 and decreases exponentially. So K0 is e minus x over square root. Square root of pi over 2x. Okay? And so it's decreasing exponentially, and here it diverges. Okay, it goes like log minus log of x over 2. Okay, well, so need some properties. So K0 is minus log root. Okay, good. Euler-Mascheroni constant, again, I'm forgetting it now. That's good. Yeah. What is the Euler-Mascheroni constant? What is the Euler-Mascheroni constant?
Siri doesn't know.
I'm not sure I understand.
What is it?
Here's what I found on the web for Mascheroni constant.
Everybody, someone get it?
0.57.
0.57, okay? And there's a definition, you can go work it out, okay? It comes from the expansion of the gamma function near its poles. All right, so, anyway, so it's actually relevant for our discussion, so it's constant. So there was a question of how do you normalize the logarithm, or how do you choose this constant? It turns out that this will play a key role in that answer. Okay? So, good. Now, so now let's see. So what do we want here? We have these formulae written down. Okay. Well, okay, so outside, we of course only want the exponentially shrinking solution, not the exponentially growing solution. So outside, what do we get? Okay, so phi out. Okay, phi out, R of k. Okay, and just to use my notation, okay, it's going to take, I'm going to call it b, okay, just so I stick with my notes, but it's just a constant at this point. Okay. And inside the solution, of course, inside the cylinder, we only want, of course, the solution which is regular, not irregular. I mean, the vessel K0 blows up. Okay, so we don't want that. So R of k inside takes the form of A of k, I0 of k and rho. Right. And so we now go ahead and now we can use our jump conditions to relate the interior and the exterior solutions. So let me put this here. okay, what do I get here? I get R of K in rho. She needs to take some form C of K as K0, KR, I0 of K rho. It's valid for, rho less than R, so R minus rho. And this one is here, K0 of K rho, I0 of KR, and it's valid theta of rho minus R. So we have, again, a discontinuous solution. One on the interior obeys one thing, on the exterior obeys the other thing, right? Okay, and so, which is what you expect, right? Good. Of course, the full solution these K's are quantized in phi of rho and Z. Sum over n. Okay. R, K, n. Okay. Cosine. Z. Okay. All right. So now we need to use finally the boundary conditions, right? So there was E rho is out minus E rho in should be the surface charge density. All right. So that should give you enough conditions, right, to determine these CKs, these unknown coefficients CK. Right? So, well, don't be timid. Okay? Just do it. Do some aggressive algebra. Helps maybe to first, so what we've done here is to break this up into a Fourier series of cosine Kn, right? So it helps, or not quite a Fourier series because you only have cosines. So it helps to do the same thing for the charge density. So let me break it up in lambda. Lambda's a constant, right? It's a constant. Let me write it as some, lambda n, right, sum over n, lambda n cosine kn. Because our solution is expanded in these harmonics, or these eigenfunctions, so we should also expand the source in the same harmonic eigenfunctions. Okay, so lambda n is here 2 or L. Okay. Integral lambda cosine k. Okay, so you can work that out. Okay, it gives you 2 lambda minus 1 n 1. In my notes, I divided here by 2 pi r, because the 2 pi r appears here. Okay, so let me do that here. So let me put there, then you get this 2 and pi squared. Okay, good.
So lambda doesn't really satisfy the boundary conditions, though. How can you expand this into cosine?
So, of course, you get all terms, right? So the picture is, I'm sure you've somehow done this, right? In live. Of course, you don't really mean that lambda goes right to the boundary. You mean that there's somehow just a little bit of a gap, right? That's what we mean for lambda. And if you start expanding it in a Fourier series, you know, it will work. You'll get like this. Right? Something like that, okay? If you start doing it. And so you basically, and that's what you see here. Is decrease very, very slowly. Right, those coefficients, only like 1/n. So you see like all of them, okay, in order to describe such a function. Okay, good. Okay, so now I plug it in, and yeah, and what do we find here? Okay, so I need to erase something. Okay. Well, okay, we got to calculate E out, right? And E in, right? And so that means taking this thing and doing the derivatives, okay? And taking their relationship between them. Okay. So I need to write this down somewhere over here. Okay. Lambda minus 1 n over 1 plus 2 n squared. Okay. Okay, so now differentiate away. Very good. Okay. Okay. Sum over n. Okay. Turns out to be -1. We've got to find the row derivative. So differentiate away. Sum over n, Cn. Okay. Okay. Sorry. Okay, so you get -Cn. And E row out gives you I0 KR. And if I look at the outcome, K0 prime, K0 prime, KR, times K, and then I get cosine K and Z. Okay, and this is evaluated at row R. And similarly, En. Zero KR. Prime K0. Okay, and as you might expect, okay, let's look at it term by term, yeah, right? So just look at the nth term. This is a sum over n, right? Okay, and the charge density is also a sum over n, right? And so what do you find there? So if I just compare term by term, right? You of course find the Wronskian of the two solutions. So you find here -Cn I0, okay? Everything K0 prime minus K0 I0 prime, okay? And this is equal to the Cn, which is equal to this minus n 2n. Okay. Okay. Okay, so you ought to expect that. I mean, unless something radical happens, that's to be expected. Okay, that you know, you're basically asking for conservation of flux. Okay, the statement that the Wronskian is kind of constant is just a statement of conservation of flux, okay? And here you see it very explicitly, you know, by getting these boundary conditions, I was implying Gauss's law. That's what we did. We did a little Gaussian jump from there to there, right? Okay, and so we see that Gauss's law, at least expressed in this eigenbasis, ends up being, you know, just a Wronskian of the two solutions, which you know is constant, okay? And that's the statement of constant flux, you know, if there's no charge there, the flux is constant. Okay, so the Wronskian is a constant, or almost a constant, okay? Good. And so, turns out to be